Hello, my name is Marharyta Aleksandrova. I'm going to present you our work entitled K-Pareto Optimality-Based Sorting with Maximization of Choice. This work was done in collaboration with Ruppert from Mathematics and Computing Science, Luxembourg, and Thomas Engel from the University of Luxembourg. In the modern era of information overload, it is often required to choose a subset of the most useful elements. This implies sorting the elements with respect to a preference relation. In a one-dimensional space, this is a straightforward task. However, when the number of dimensions is growing, it becomes more and more difficult. Let us consider this example with two utility coordinates, color and size. There are multiple ways to sort this set. We can do it with respect to size or color. We can also use the traditional Pareto dominance-based sorting, or we can sort by k-Pareto optimality that will be discussed in details later. Given such a variety of sorting, we can use a criterion to choose one of them. One possible criterion can be maximization of diversity or choice in the selected subset of a given size. This criterion can be useful in different practical applications, for example, recommender systems, genetic algorithms, scheduling, and others. To the best of our knowledge, sorting with choice maximization was not considered in the literature before. We introduced the concept of k-Pareto optimality that is the key to the solution of the maximum choice problem. Pareto optimality of an element X from a given set is defined as the measure of a set of other elements that are strictly preferable to this element X with respect to a predefined dominance relation. This dominance relation is used to define which elements in the set are better and which are worse. There are no restrictions on the set of elements. It can be both discrete and continuous. Also, there are no restrictions on the measure that defines the size of the set and its subset. It can be, for example, the traditional counting measure when we count the number of elements in a set, or a probability measure defined on a set of events. Formally, the choice is defined as a measure of incomparable or equally preferable pairs of elements in a subset. For example, for counting measure, choice in this set is equal to 1, and in this set it is equal to 0. In our paper, we also show that choice is functionally related to diversity. We formally prove that sorting by k-Pareto optimality is a solution to the maximum choice problem. That is, it maximizes the choice and thus the diversity of a chosen subset of a predefined measure. As a direct consequence, we obtain a novel characterization of the arc of hyperbola. Among all descending functions delimiting an area of a fixed size, the arc of hyperbola provides the highest probability of the event that 2 points randomly chosen from the delimited area are incomparable or offer choice. To demonstrate the usefulness of sorting with choice maximization, we consider its application in genetic optimization. We hypothesize that maximization of diversity on the selection step of genetic algorithms will result in larger gene diversity and will allow exploring the search space more efficiently. In our experimental evaluation, we replaced the traditional Pareto dominance-based sorting in the well-known NSGA2 algorithm with sorting by k-Pareto optimality. We used two different measures, counting and probability measure, what resulted in two versions of the algorithm denoted by PO count and PO prob. The proposed methods were evaluated on the 0-1 knapsack problem with independent objectives. The results averaged among 30 independent runs were compared with that of NSGA2 and NSGA3. Our results demonstrate that the proposed method with probability measure allows increasing the value of hypervolume by up to 60% as compared to NSGA2. Also, in the case of this measure, we can develop a computationally efficient version of the sorting procedure, which is considerably faster than other analyzed algorithms. Our code is also available online. As for the perspectives of the future work, we believe that further theoretical analysis can allow us discovering new interesting relationships. Also, the developed theory can be used in other applications, such as constraint genetic optimization, optimization of complex structures, recommender systems, and development of non-parametric statistical tests.